So, thank you so much for coming. This is the second FHE Summit that we're hosting. The first one was in Brussels. And the goal here is really to, unite all the builders, investors, researchers in the space, and push for the development of FHE in the Web3 space. Thank you for our sponsors. So Zama, Hexens, Inco, Primus, and My Network. And just to say, since the last time we presented FHE Summits, FHE has gotten a lot more traction in general within the privacy space. So this was a report done by AllianceDAO. As you can see, FHE really is starting to take off, right? Especially compared to a year ago. And other privacy technologies such as ZK, MPC, TEs are also, very top of mind and has been around for quite some time. But just wanted to, note that, FHE is becoming more popular and is becoming top of mind. The second thing is FHE is starting to make into enterprise as well. So some of you might have seen that Apple announced Swift homomorphic encryption. And so they're using basically FHE for their iOS 18. And within this, there is something called live, I believe it's called live caller ID. The idea is that you want to look up for information about a phone number without necessarily revealing who you're looking up to, right? And so what they're doing is they're using a scheme called BFV, and this is already production ready. This is what they're already using today. We presented, Web3 use cases about FHE at this annual summit in Salt Lake City, where a group of leaders from Google, IBM, Intel, also NIST were there to discuss about commercialization about FHE, and I can tell that there's definitely a lot more interest in getting to Web3. So having FHE basically provide value to the Web3 space. So far, a lot of the FHE explorations in Web2 has been more around enterprises, healthcare data, private sector intersection. But Web3 definitely is getting a lot of interest now in the FHE space. Our friends at Zama actually released a report recently as well with JP Morgan, really around how do you utilize FHE for asset tokenization. So you can think of fund tokenization, but also secondary market trading, right? So institutions are also starting to notice about FHE and how you can use this in the blockchain space, and specifically around the idea of identity, compliance, and fully on-chain, essentially. And that has been, I would say, historically a pain point for enterprise to do all these things fully on-chain. And FHE does provide a quite differentiated angle here. And we also launched a white paper with Circle last week around this idea of confidential ERC20. I'll speak a little bit more about this later today. But essentially, privacy or private payment has always been a pain point in the Web3 space that hasn't really been solved. And so FHE does offer differentiated angle here that makes it quite interesting for folks to explore. And so just from a high level, what we'll have is we'll have some morning keynotes. We'll have a lunch break in the middle, and then we'll have more keynotes, workshops, and panels in the afternoon. And so we do run a podcast called FHE on Chain. If you're new to FHE, we interview a lot of the founders and researchers in the space, so great place to get started. If you're interested in working with us, here are the links. We are looking for partners, whether you're a builder, researcher, or just want to be part of our ecosystem, definitely reach out. So I'll quickly talk about Inco. What is Inco and what we do. So what we're building in Inco is what we call the Universal Confidential Computing Network. So today, all the L1, L2s have one thing in common, is that they are complete transparent databases. So why is that a problem? It's a problem because if you want mass adoption, you need a minimum confidentiality. So I can give a couple examples. Today, if you use crypto as your bank account or for payroll, everything's transparent. But this is not how Web2 works. In fact, if you were to onboard 1 billion people to crypto today, it would actually be social chaos because everyone can see everyone's bank account, right? Second is institutions and enterprises are still having a hard time entering the space. And the reason why they're having a hard time is because they've tried private blockchains, such as Hyperledger, R3 Corda. They're not quite the same because these essentially don't interoperate with the public blockchains where all the users are at, right? And then lastly, there are just a lot of use cases that wouldn't make sense without confidentiality. So if you think about private voting, the card games, you need some confidentiality, some hidden information in order for these use cases to make sense. So we utilize FHE. So I guess folks here are already quite familiar with what FHE is. But for folks who are non-technical and first time hearing this, the idea is that you can compute on top of encrypted data without knowing what it is, right? And so imagine if you had a cat picture, you're able to encrypt this picture and still compute, right? You can modify the pixels, you can add, divide, multiply, modify the RGB values, and by the time you decrypt, now you have a filter. It almost sounds like magic. So FHE is now new. This concept has been floating around for the past 40 years. First started in the 70s with this idea of privacy homomorphism. Back then, it was just a wild idea. Like, what if we could encrypt data and also compute on top of it? The first, I would say, somewhat valuable proof was around 1999 with Pascal Paulier, who come up with a partial homomorphic encryption where you can do simple additions. So at least that was like the first tangible proof that something like this could be feasible. It was really until 2009 where Gentry came up with this idea of bootstrapping, where you can start doing more complex operations, and then do a bootstrap to reduce this noise overflow problem. So 2009 was a big turning point, and then 2021. There has been breakthrough around the FHE cryptography that makes this bootstrapping a lot more efficient. So back then, 2009, bootstrapping was taking a lot of time, still making it difficult for practical reasons. Now you can do this in tens of milliseconds, a lot more faster. And then specialized FPGAs are also coming out to the market very soon, which is the path for accelerating FHE. So we utilize the TFHE scheme. So there are many schemes around today. The reason why we use the TFHE scheme is because it has a couple properties that makes it a lot more suitable for smart contracts. And so first is it has a very broad range of operations. So you can add, divide, multiply, you can do comparisons, which in the context of smart contract is very useful because what if I want to build a private AMM? What if I want to build, let's say, a private voting? I need to be able to express different logic using different operations. Second is it has exact computation. So what do I mean by this? There are other schemes in which you could do more complex operations, but what you end up is an approximation on the results. So this could be fine for things like machine learning because you could train the model to absorb a lot of these approximations, but in the context of smart contract, you don't want to end up having more money or less money or getting liquidated because the computation is not exact, right? And lastly, it's a non-level structure. So a lot of these schemes, other schemes, basically you have to define ahead of time how many steps, how many operations you need to do ahead of time and do a big bootstrap at the end. With TFHE, what you get is the ability to do bootstraps very efficiently in between operations, so you can keep on computing over and over. And so if you write smart contracts, you don't necessarily know ahead of time how many steps there will be, right? So this is why overall TFHE scheme makes a lot more sense for the context of smart contract. And so there has been attempts to privacy in the past. I would say there are two major types of solutions. One is commitment-based. The other one is encryption-based. So commitment-based, you can think of all the ZK approaches, so Zther, Zcash, Tornado Cash. Encryption, you can think of MPC, FHE, even TEs. There are quite differentiated properties here. So in terms of compute overhead, commitment-based solutions usually do state transitions on the client side. Then they generate a proof that's verified on chain, and then the state transition happens on chain afterwards. In the encryption-based system, the blockchain itself actually do the state transitions on behalf of all the users. So a little bit different here. In terms of privacy, you could argue commitment-based is more private because every single user has their own secret key, and the secret never leaves the client, the browser, basically. On the encryption side of things, typically you would depend on a trusted party. So this could be MPC-based, but everyone encrypts under the same trusted party. But what you do get is more flexibility around the decryption rules versus in the ZK system, what if you need to delegate your viewing key to, let's say, an accountant to do your taxes, or let's say a auditor, right? It becomes very rigid and difficult. And lastly, there is this concept of private state composability. So what do I mean by this? In ZK systems, every single application is siloed because all the circuits are stored off-chain. They can't really talk to each other over the private states. In encryption-based, it's different, right? Because we're all doing state transitions over encryption, so cryptography. And so people can interact with the same states over and over and have a more seamless experience, I would say, with this idea of composability. And then lastly, key rotation. Because everyone has a viewing key, it is, like I said, more rigid. But in the encryption side, especially around FHE, you can also do key resharing, key rotation, making this process a lot more flexible. So we did release a research with Circle research last week, and the finding here was really on 3 points, right? So what makes a confidential ERC20 stand out compared to legacy payment solutions? It's really around this idea of flexible decryption rules. So you can imagine from an institutional perspective, they want to be able to have more flexibility in, let's say, investigating or delegating, the decryption to, let's say, an auditor, or even you as a user delegating to your CPA to do your taxes, right? The second point is around composability. So I'll touch upon this a little bit more later on. And lastly, is programmable transfer rules. So what you get here is, with FHE, is the ability to compute, but also do comparisons. So you could have on-chain identity that's fully encrypted, FHE-based, and customized transfer rules fully on-chain. And so this could be applied to stablecoins, protocol tokens, also RWAs. So on composability, there are 2 points I would like to make. So one is the idea of end-to-end confidentiality. Today, if you were to build, let's say, dark pool, you actually leak information just by transferring money into the dark pool system, right? But what you get here instead is, if you have a confidential ERC20, you can actually just directly move a confidential amount into the dark pool, which gives you the end-to-end privacy, right? The second thing is around this idea of extensibility over shared private states. With a confidential ERC20, you can use that to cast a private vote. You can use it for payments. You can use it for lending. Again, because of composability, you can essentially extend on top of confidential ERC20 and build more useful things. And this is a stark contrast to, I would say, ZK-based systems, which are less composable, in which oftentimes people build very siloed applications. So when you apply FHE to the EVM, what you get is a couple of things. So one, you get new data types. So this idea of encrypted integers, booleans, addresses. You also get to do operations on top of these encrypted data types. And so here, you don't need to write complex circuits. Everything is abstracted away. You don't need a centralized off-chain coordination layer, because there's no prover, right? Everything is happening on-chain. And then we also offer native randomness that could be quite useful for poker games, for example, for generating cards. So what Inco is really building here is what we believe to be the missing layer in the blockchain space. So you have folks like Celestia building DA as a layer. What Inco is really providing here is the confidential computing layer. And so with this, we do believe that this is the next frontier. We can enable net new use cases that wouldn't exist otherwise in Web3. And so we do this for existing blockchains across different verticals. And we come up with a novel architecture here where we do provide storage of ciphertext. We provide the confidential computes. We have our own consensus layer here. And then the idea here is Inco is a layer that sits on top of existing blockchains to essentially extend the capability for them to perform confidential compute. And we do talk about FHE quite a bit, but in reality, we do also use ZK and MPC, but for different purposes, right? FHE obviously is used for all the state transitions, all the computes. MPC is used only for decryption. So this is actually interesting because what we're using is actually something called threshold FHE. It's actually not just pure FHE. And what the benefit you get from here is by decoupling the decryption from the compute, we can actually go much faster over time. Because FHE compute doesn't require communication between the nodes, you can always have better hardware to make this go faster and faster and faster over time. And decryption is also rare, right, in the context of smart contracts. So this is why by decoupling both, we get to go much faster on the long term. Where we use ZK is on the client side. So you need ZK to prove 2 things. One is that the ciphertext, when you encrypt data on the front end, is not malformed, because that could cause issue for compute later on. The second one is around the fact that you know what the plaintext is. So why is that important? It's important because what if someone grabs your ciphertext by looking on chain, deploys another smart contract, and then decrypts it, right? So this is more of a, I would say, security mechanism here. And so we offer the most intuitive way for folks to directly build on top of existing blockchains using FHE. And you get a couple of benefits from here. One is you get to tap into an existing user base that already exists. We're not saying, hey, come to our layer 1 or layer 2. We're saying we'll meet you halfway, and then you get to build where you're at already. Second is there's just a lot more TVL and adoption that already exists. And so you'll get to directly write this FHE code in a seamless manner. And Inco is abstracted away. A couple examples of use cases. People often ask me, what can you actually do with this, right? So confidential ERC20 is a very simple example. For folks who know Solidity, today your address is just a mapping of your address to a plaintext amount. But what if you can have an encrypted amount for your balance? And when you do an ERC20 transfer, you are essentially transferring a hidden amount, right? So when Bob sends money to Alice, only the amount is hidden. And so this is actually not touching anonymity. It's actually the opposite. What we do is confidentiality, meaning that we only hide specific metadata here. And the metadata here is the amount. So this is very similar to like a Venmo or Revolut experience where you see your friends sending money to each other, just not the amount, right? Another one is, on-chain poker. So, isn't crazy to think that crypto still doesn't have fully on-chain poker? The reason why is, you need randomness. So we have VRFs through Chainlink today. However, they are plaintext VRFs, so you can't really use that. Poker is a bluffing game. You need to be able to hide information. Luckily, with FHE, you are able to generate random integers over time. So here you can use this to generate cards. We built a fully on-chain Mafia game a year ago. This was also a proof of concept. Here again, you could be a secret killer, doctor, or detective. It's a bluffing game. You need hidden randomness. One thing that's interesting also is if your intents are encrypted, bots cannot really front-run you, right? Or they can try to front-run you at a cost and risk, right? So this is kind of what you get with something like a private AMM using FHE or any encryption-based system is that the inputs will be encrypted, so very difficult for people to front-run you. And then private voting is another good example of why you need shared private states. It's really because everyone can directly cast the votes to the blockchain layer that acts as this coordination layer, which in the case of a commitment-based system, you kind of need a prover to coordinate the states and tally everyone's hidden votes. But because ZK cannot do state transition over encrypted data, it has to be over plaintext, right? So there could also be information leakage here. So we are compatible with the existing Ethereum tooling. So Hardhat, MetaMask, Remix. It takes 20 minutes to onboard, which is very easy for folks to build. As I mentioned before, by using the TFHE scheme, you are able to support a pretty wide range of operations. So it's really your time to unleash your creativity, right? So if you want to build a private AMM, a voting application, any gaming, by having access to divisions, bitwise operations, all sorts of comparisons, this becomes a lot more expressive and easy to build. And yeah, lastly, if you are interested in learning more about us, here are the links, and then our team members are also here, so feel free to come say hi. Thank you everyone for coming.